Okay, so hello everybody. I am Krishna, um, and today we'll be looking at possibly one of one of the most spectacular methods or approaches to looking at combinatorics. So the 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 main part, the main thing that's good about this method, the symbolic method, and in general, the field is called analytic combinatorics, is the sheer generality in the sense that everything is unified in a sense. So we'll see more examples of that later, but it can cover all sorts of things that a simple counting argument may not be able to do so easily. In a sense, the results. So one thing to be warned about is that it might look too easy. So just be careful and make sure you understand the argument, because it's going to be like almost immediate, the results this way. Okay, anyways. So how many people are comfortable with generating functions? Okay. Okay, so it looks like a lot of people are familiar. Okay. In any case, I'll be revising it once. Just give me a second. Okay. So a formal series is an infinite series of the form okay. So if z equals that. So the thing to note is that z is not to be thought of as a variable, in the sense that it's not like you could put half and look at whether this series actually has a value or not. It's not about that. So here ans are real or complex, whatever you'd like. So the thing is, z, meaning the variable z, is kind of just a placeholder, in the sense that from f of z, if you know the whole form of f of z, you can get each of these coefficients an. That's the basic idea. So because different powers of z don't mix with each other essentially. So if I told you this right hand side, just as it's sort of like a polynomial but an infinite polynomial, if I told you this, you'd be able to tell me each one of these coefficients. So that's the useful thing. Okay. Addition and multiplication of formal series. So addition is quite simple. So what we can do is we can say fz, this particular expression, is the same or very similar to this sequence, right? And you can exactly see that, right? Okay. So they're one and the same, as in from f you can get the sequence, and from the sequence you can construct f. So fz plus gz, let's say f is a0, so on. Usually I'll just call this an, right? Where it is understood that n equals 0 to infinity. I may not write that sometimes. And suppose g is bn, which means g represents the formal series for this particular the set of coefficients bn. Then you define fz plus gz is another formal series which represents the sequence an plus bn. And what is this sequence? Is just a0 plus b0, a1 plus b1, so on. Okay. Simple enough. It's just like you could treat it like a polynomial and use the usual rules of addition, right? Okay. So and multiplication is also how polynomials would work. So again, if f is an and g is bn, then fg or f of z, g of z is a formal series h of z, where h is c0 plus c1z. So I'll just use this notation again. Then we have, so think about it. Suppose you were writing c0 plus c1. So you want h of z equals fz gz, and suppose it would be nice if the usual polynomial multiplication rule happens. So you would say c0 plus c1z plus c2z square plus so on must be equal to a0 plus a1z plus a2z square plus a3z cubed, so on, b0 plus b1z plus b2z square, and so on, right? So suppose polynomial multiplication held good, then could you see that c0 is in fact the same as a0 b0, right? I assume this is clear. Someone just
Yeah.
and c1 is a1 a0 b1 plus a1 b0, right? Because the only ways you could get z as a total. Remember, I told you that the power of z like essentially singles out the coefficient. You can't add different powers of z. Z is not a variable, so it's not like, I mean, saying z equal 1 and then you can do c1 plus c2. No, I mean, z is just a separator. So you see that the only ways in which you could get z on the left hand side from this particular product, assuming polynomial works, is if you take a constant from here and multiply it with a z here and or a z here and a constant here. So this coefficient just becomes a0 b1 plus a1 b0 z plus, right? So this product evaluates to this. So far we've seen. What about z square? Either you take 2 degree 2 degree 0 degree 1 degree 1 or degree 0 degree 2. So this essentially becomes summation k equals 0 to 2 of a k b 2 minus 2, right? Times z square. Is this clear? The summation, right? I just said take a2. Okay, k equals 0. So a0 b2, a1 b1, a2 b0. So do you see that in general, if I have to get z to the n on the left side from this product, that means either I take 0n or 1n minus 1, only then the z's will multiply. So k equals 0 to n. This is correct? 0n, 1n minus 1 all the way up to n0. I assume that's clear, right? This particular experiment. Yeah. So essentially this is how, so now what we did is we want polynomial to work, but I mean we have to define product because f and g are some different things. They're not polynomials. They look like polynomials. So you just say that f of z, g of z is a formal series h of z, where h of z demarcates the coefficient cn, where each cn is given by this particular relation, right? So this is your definition. And then what this means is you can just look at it as polynomial multiplication and you'll get the same result. So you don't have to go by the definition. I mean, if you're given f is like x, z plus z square and g is 1 plus z cube, then you don't have to do c0 is a0 b0, but a0 is 0. This c1 is what, just c1 is a0 b1 plus a1 b0, but a0 is 0, so this cancels. A1 is 1, b0 is 1 equals 1. You don't have to do this. I mean, you can just multiply them. And since we just saw that this multiplication gives exactly this, it's all right. You'll get the right answer for the coefficients here. Is everybody with me so far?
Yeah.
If someone hasn't understood, you can raise your hand. Happy to. Okay. Cool. So now we look at what a generating function is. So one final thing, if you have a formal series Fz, which demarcates the sequence Al, then you write An equals, where this notation means the coefficient of z to the n. The coefficient of z to the n is exactly an, because nothing else has a z to the n multiplied with it, right? It's a0, a1z, there's only an an zn. All of these don't count in zn, none of those as well. So essentially, if you know the form of f, then you can just find the coefficient of z to the n and that will give you an. So in a sense, fz encodes this perfectly. So why we exploit this and how we use it is by this following example. Suppose you had to choose from some number of red balls R and some number of blue balls. Okay. And you want the total number of balls to be 3. In that case, how you would, the number of ways you could do this is, you have an infinite supply of each, is of course, 4, right? Because either you pick 0, 3, 1, 2, 2, 1, or 3, 0. So the thing is, what if you had to do this? Okay, wait. So what you can do is, you just said that the answer, the answer is the number of ways to pick 0 red times the number of ways to pick 3 blue, right? 3 minus 0 blue plus this 1 and this 2, right? 2, 1, and 3, 0. This looks really similar. It's the same thing as the product of generating functions, product of formal series. So in essence, if I had a formal series R of z, which had its coefficients as the where like the first coefficient was number of ways to pick 0 red, and the second coefficient was number of ways to pick 1 red, and so on. In this case, there's only one way to pick either of them. You just pick them. So this will just be 1 plus z square, so on. And similarly, blue is also the same, right? Then do you see that the number of ways to pick 3 balls overall, like from red and blue, is just the coefficient of z to the 3, which is a total of 3. This thing should sum up to 3 of rz bz, right? Because you know your answer is exactly a0 b3 or r0 b3 plus r1 b2 plus r2 b1 plus r3 b0, right? So your answer is exactly this. Why is this useful? Because you don't have to actually go through this casework. Multiplying formal series is going to result in that sum which we saw for the coefficients, from which you can easily get the answer. So that sum and all the ways to get this z power 3, which is a total of 3 balls, all of that is encoded in this product. You don't have to worry about each case, right? So it becomes much easier. You just find this, multiply them like normal polynomials, and then just find, in this case, this polynomial looks like I'll show you how you get this very simply, but it looks like this. So your answer is 4. No work done. And you can look at it directly. 1 z cube, z square, z cube 1. That's the only way in which this r into b will give you a z cube term. Okay, so you see this multiplication thing for formal series is quite useful to encode like selecting a total from some choices. Just write down the formal series for each choice and be done with it after multiplying. So this is why generating functions are useful, and generating functions are exactly based off this idea. So a generating function for a sequence an is essentially the formal series summation this, and all those rules apply. We will define where we'll use generating functions just a little later when we look at the symbolic method. But there's one last point about generating functions and formal series that I wanted to address. So since you can multiply two, okay, so what's the identity for multiplication of formal series? So an identity is an element A such that A into anything is the same thing, right? So if you look at this being a formal series, then what formal series A is there such that you multiply it with anything and it gives back the same thing. So of course that formal series is 1 plus 0z plus 0z, whatever. The sequence 1, 0, 0. Because of course by polynomial rules, that multiplies to give the same thing. So now there's this notion of an inverse, which means if I give you a formal series F and I ask you for a formal series G such that this becomes 1, their product becomes 1. Is it possible for you to give such a G? That's the question. So consider the following. If I say F is the R sequence that we just saw before, all coefficients 1, right? G is 1 minus Z. Consider this. Then what can you say about F, and let's say Fg is equal to H, then you have Hz is 1 minus Z times 1 plus Z square plus so on. Oh,
This should be one,
multiplication.
right?
Huh?
This should be one. Because
it-
like you can write the right side as 1 by 1 minus z. Oh, I
Z
mean like 1
is,
plus z square can be written as 1 by 1 by z, 1 minus z.
why is it 1 by 1 minus Z?
That's the generating function of that thing.
No. Why is this 1 by 1 minus Z? I mean, do you have a proof?
Oh right, GP.
No. The thing is, Z is not a variable. So
Oh.
there's no GP yet, right?
Oh, so I think what you do is like you can check for each term manually, and then you will get that this thing is 1. So then you
Exactly. So it in for generating functions, the problem is you could have a generating function of this form, right? And we'll look at this generating function a little later, but you could have a generating function of this form. But if you think of Z as a variable, I agree, it is easier to place the rules as you first see it for generating functions in terms of Z being a variable, in which case all of this is like obvious stuff. But the problem is when you have something like this, if Z is a variable and the sum makes sense, then Z has to be 0. Any non-zero value of Z will make this blow up to infinity. And then you can't really do any additions, multiplications to that. Addition and multiplication breaks at infinities. So you'll get like, I mean, one simple example is infinity plus 1 equals infinity plus 0. That's correct. But like if you play around and just treat infinities as numbers, you'll subtract infinity on both sides and get contradiction. So we don't want that. So you have to introduce it. But this kind of stuff is useful. And I mean, frankly speaking, you don't want to look at convergence issues. Right? So for that, like the whole point of generating functions is to be able to encode a sequence. We want to encode this kind of sequence. So you can't treat z as a variable, essentially. It's like a reverse argument. So indeed, you're correct that we'll show that this thing is 1 by 1 minus z. But essentially the argument is copying the GP thing, but without using the fact that z is not a variable. So essentially what you will show is this thing. You know how to multiply the formal series. It's just like polynomial. We have already defined it that way. Minus z square minus z cube, right? Polynomial multiplication we've shown. So we can use that. So this is 1, right? All other coefficients, all other powers of z have a 0 coefficient. Right? So this is essentially this 1, 0, 0, 0 sequence, or just 1. So what this means is that the inverse of this, which I called f, is this. So is everyone with me? You see why this is not a contradiction, but like you can't really use GP.
Yeah.
Okay, fair. It's a bit of, you just have to be careful not making some assumption. But yeah. So now what you do is, for reals, you have this thing that the multiplicative inverse of 2 is 1 by 2. Right? So actually this is some number, right? And you call this number 1 by 2. You call this number 1 by 2. Why? Because that's how we write it. In a sense, you know that there's an inverse. What do you call the inverse? 1 by 2. To kind of like move the 2 below. I mean, it's just some notation, right? That we are all comfortable using. So obviously you would like to use this thing. If G is the inverse of F, you would like to use this notation for F, for G, right? Or very simply put, since if G is the inverse of F, then F is also the inverse of G. You want to write this. So you define, again, this is definitions that will allow us to do stuff as if Z were a variable, right? You cannot, Z is not a variable, but most results that apply if Z were a variable do apply here, except these convergence issues. You have to take care of that. Indeed, there are some Olympiad problems that will get some generating function like this and put a value. But you can do that only when you're sure these things converge. Right? Okay. So essentially, what I said is define. So more correctly, you would write F inverse is 1 minus Z. Right? This is the way you denote the inverse of this 1 plus Z, which I called F. But instead, because I mean, if you have to write 1 by 2 somewhere, you won't write 2 inverse. It's just more used to and more natural to write 1 by 2. You define this notation 1 by F to be the same as F inverse. Clear? So essentially, what you write is, you know that the inverse of 1 minus Z is 1 plus Z square, this thing, which we have shown. I mean, these two just multiply to 1. We've shown that by the multiplication straight. And now you know that you can also write this as 1 by 1 minus Z. You see the parallel between the GP proof and this, right? The GP proof is essentially this. It's exactly the same thing. You call this as S and then you do ZS is this, and then you subtract S minus ZS and then all these cancel. It's the same thing, but we only assume multiplication so far. So we'll have to prove it from scratch and use this notation. For real numbers, this notation is somewhat implicit. I mean, in particular, you're actually introduced to 1 by 2 before you're introduced to 2 inverse and the notion of powers. So here, for formal series, this is what you're actually using. 1 minus z is a formal series. 1 minus z has an inverse. That inverse is this long thing. It doesn't matter if it's infinite. Formal series are infinite. So now you can write this as 1 by 1 minus z to give that analogy to our GP thing and how we write real numbers, reciprocals as this. Okay. Okay. Is this clear so far? Because once you've understood this, a lot of generating function manipulations become easy, because the key thing is, instead of extracting information from an infinite series, you can write it as this, and like this is much smaller to handle. Cancellations are easy. I mean, if you have something like this, some weird stuff, you can just cancel one. So this notion of inverse and writing it in this form makes it more suggestive to cancellation. Either way, just notation. But I hope you guys get the idea of what we're trying to do. Z is not a variable, but we are allowed to use these things provided we can show them from what we have so far proved or defined. And we're getting these closer and closer to how Z to the case where Z is a variable, but not quite. For example, we can still do this, but we can't do that if Z were a variable. And okay, I hope it's clear so far. So there's an interesting exercise that you can try later, which is to show that if f has its first term 0, which means if f is a1z plus a2z square, a0 is 0, then okay. So is it clear that if f is of this form, a1z plus so on, as in the constant term is 0, then I can never multiply this by some g which is b0 plus b1z so on to get 1. That's clear, right? Because it will start with z and there's no constant, right? So the constant on the left hand side is 0, or I mean a0, b0, a0 is 0, and the right hand side is 1. So you see that anything which has its constant term 0 is not invertible. You cannot invert it. You will have to grind through whatever long thing to get results, whatever you were trying to manipulate about the generating functions. But the interesting thing is, if the coefficient is non-zero, then you can invert the thing. So like essentially you have this choice, right? You have b0, b1. You can choose whatever you want. You have to get this to 1. Very simple. I mean, this you choose as 1 by a0 so that constant term matches. But now you have to get that z term to 0. So if this is b1, then you want a0 b1 plus a1 b0. b0 is 1 by a0 is 0. So then you'll get something for b1. And then you do the z square. You'll get something for b2. It won't be very nice, that expression in general. But you'll get something for b2, which means that indeed I can find some coefficients and this will be 1. That's all we care. It's invertible. So many times we'll just be using this, that okay, it is invertible. I don't care what it is, but it is invertible. Okay. That's all for generating functions. Probably a little long prerequisite, but yeah, the symbolic method is essentially only generating functions. Like their working is essentially generating functions. So important that we understand that well. Okay. So now, okay, I assume everybody is following, right? Because this will all be useful, and now we'll get to the cool part.
Yeah.
Okay. Okay. So a combinatorial class, for some definitions so that we can talk using these and I don't have to spell out the whole thing. Is a finite set. Finite or countable set. Right? With the following properties. A, there is a size function which I'll denote like this. I mean, could have called it size of x, but I'll call it this because we're just used to, like for a vector, we are used to this notation to denote length and stuff. So we'll just continue with that. There's a size function on the elements of C, a combinator as a C is a finite, C. There's a size function on the elements, and the size function returns only non-negative integers. So it takes elements of C to non-negative integers, and the number of elements gamma in C with size equal to K is finite. Nothing much. We're just saying that you can't have infinitely many things mapping to the same size. There's only a finite number of elements of each size. Yeah, and C counts like all kinds of sizes could be there. Okay, so we'll take a few examples. So these are like almost obvious restrictions. Let's see. So let's see some examples. So the first thing is there's a size function, and secondly, finite image of size n. Finite. Okay. So an example is the class of all integers. So the integers, I'll actually call them I. Yes. Or even more simply, all non-negative integers. So 0, 1, 2, and I'll define size of I equals I. Fair enough. I can define this thing, the size function. So it's clear that there's only one element of a particular size. So those are satisfied. This was somewhat a trivial class. So suppose I remove this restriction and say all integers, so it's -1 and so on. Then size I'll define as modulus, right? That works. There's only 2 or 1, 1 for 0 and 2 for the others. One element of a particular size K. So why I needed this mod is because size is non-negative. And I mean, you would imagine, I mean, I don't want an object of size -1. So like this, it's we would like it to be as close. We would like our definitions to be as close as possible to what we are used to. We're used to things of non-negative size. Of course, if need be, we'll change that if it's actually useful. But in this case, it's not. This is more intuitive and more useful as well. So now we look at a more non-trivial class, a class of all permutations. So essentially, here the object gamma. So this class is called P, the object small p. So some notation first. Write this on the side. If a class is A, I'll denote it by cursive A. Sometimes if I'm lazy, I'll just put this normal capital A, but usually cursive A. And the set of elements of size n in A, I'll denote by this or an. Okay, it's also a set. And of course, it has a size function defined on it, and you can just take the same size function, and there are only elements of size n. So this finite is also there. So an is also a class for every n. Is just a note. And the number of elements of size n, which is just this, will be called an. Okay. That's for notation. So, and also an element of A is usually denoted by its Greek equivalent. So alpha. Okay. So for B, beta, that's why I use gamma for C. Gamma is the third letter. Yeah, but sometimes, I mean, yeah, for P I should ideally use pi, but we won't assume that much familiarity with Greek. In any case. So let's say P is in P, then P is something of this form. P is a permutation 1, 3, 4, 2. Okay. This is an object. So it's something. So, and what do you think the size function is for an element? So P is the set of all permutations, all of these kind of things. They don't have to be only 4 elements long. Even the empty permutation counts. All permutations of size 5,000, like of 1 to 5,000 also count. So what do you think is the size function? You can reply in the chat.
Probably the length of permutation.
Yes. So you see that these are quite natural. I mean, they'll occur in all kinds of things. So that's one class. Okay. So now we have, okay, let's get another class. What is it? The set of binary words. So the set of bit strings or 0 1 strings, or whatever you'd like to call it. This sequences with only 0 and 1 binary strings. So W. So an element small w is something like this. So of course, I mean, I'd like people to actually respond in the chat so I know you're following, because it's quite nice and I'd like people to understand this well. So what's the size function?
The number of like bits.
Yes. So so that will, there's the obvious size function. And you see that that's a class, right? There are exactly 2 to the n of size. So now given a class W or given a class C, you associate a generating function with the same name. So it's also called C, but C of Z, to make sure that it's a generating function. Sometimes that Z is even omitted when the context is clear, but yeah, C of Z is this. Is defined to be this formal series or generating function, where I've already told you what these small things are, CNs, right? So for the permutation class, P of Z is our friend from earlier, this guy. And for the words, what's the generating function?
Or what was P of Z here?
P was the permutation, the set of all permutations.
Oh, okay.
Right? So the number of elements of size n is exactly all permutations of 1 to n. No others have size n. So it's n factorial.
So words one probably should be 26 to the power n Zn.
Yes. Or whatever we call bit strings or 2 to the n, but yes, in general, that we'll look at that later. That will also come. So it's just this. Correct? This is the generating function. You see, we've used the inverse here, this notation. So 1 by 1 minus 2z is again not a fraction. 1 by 1 minus 2z is another name for this. Right? Don't want it to be an infinite sequence. We'd like it to be like that. Okay. Yeah. So of course we can't treat z as a variable, otherwise these things will blow up. But yeah. So I assume people are comfortable with this. Now more interesting things. So here is the power of that. So you define the product of two classes to just be their Cartesian product. Where, okay. So, and if I define the size function on these tuples, right? So now these pairs are the elements of A cross B. I'll call A cross B C. I want C to be a class. So, I mean, it already has it has a countable number of elements, so that's all okay. So I define the size on elements of C. Elements of C are these pairs. I'll define them as, right, where of course it's understood that this size of alpha is with respect to this AS size function, because alpha is in A. Right? Okay. So similarly, right? So I'll define this, and it's clear this is greater than 0, and what's the number of elements with size n? So Cn, right? That's the thing. So Cn is the same thing what we looked at. Either it's all alpha with size 0 work, then I'll need to take all of these with size n plus a1 bn minus 1, so that this sum is n essentially. Is exactly this. Okay, so now do you see what? So from the greater equals 0, so since all these A's and B's are finite, all the C's are finite, so C is a class. And from now on, I'll leave you to verify that it's a class. It should not be too difficult to see. Okay, so do you see a connection between the generating functions CZ, AZ, and BZ? Do you see something?
A generating function between what?
Of A, B, and C. You know the coefficient. So
Yeah, like it is a generating function. Like CZ is a generating function, right? In some way.
see, I mean, it's that generating function I defined, right? If you have a class C, then C of Z is summation C and Z, and that's the generating function. It's called, I mean, the associated generating function to the class. Right? Because note that the encoding of a class into its generating function exactly tells you how many elements are there of every size. Because from a generating function, you can pull out every coefficient. But the structure of each element of the class is lost, because you only know its size now. You don't know, I mean, you don't even know its size. but you only know how many there are of each size. But I mean, in counting problems, you only care how many of the are there. You don't care what they are. So it's all right. Yeah. Yes, that is right. CZ equals AZ BZ exactly, because you have CN is exactly this, right? So this is exactly the definition of a product, right? Or I mean, if you want to be very formal about it, you look at this AZ BZ. Every coefficient, like the n z power n coefficient in AZ BZ is this, which is the same as the z power n coefficient in ZZ, which by definition is Cn. So they are equal, the functions. Yeah. So you get this. It's kind of the notation is quite good in the sense that if you say 6 equals 2 into 3, this notion is suggestive of that. And like, in fact, the generating functions also like multiply, so that's quite nice. It all came to the size function. Basically, this was a good size function to choose. Okay. Now we look at adding generating functions. I mean, adding classes. So the problem is classes could have, so you have a class A and you have a class B. So suppose A was just these and B was like 3, 4 and some graph. Some other thing it was. You could, so these are two sets. You want some sort of plus on them. And ideally, you would like that the generating functions add. We'll see why these are useful things later when we count. But yeah, for now, I would expect or I would like that CZ is AZ plus BZ. And let's say this has size 1, size 2, size 3, size 3, size 4, size 100. Okay. Some things, I mean, I can define whatever I want. So you would like that these two size 3s add up. So if you were to take a union of A and B, as I said, so you can take a union. The problem is that this 3 will not be repeated. And so if you write this, you'll get 1, 2, 3, 400. So this generating function is z plus z square plus z cube, one of each, right? This is z3, z4, z100, and the other terms are 0. So you would expect a 2z cube term here, right? In AZ plus BZ. But this 2 is going to 1. And you're actually losing some structure. In the sense, you don't know these. And that's very bad. I mean, that's not a nice thing to have if you look at the applications of these, this plus, which we'll see. So what we do instead is we use the following dummy class in a sense, but it's like the most useful class. It's called E, and it's just this class with some element epsilon, where epsilon's size is 0, right? So what's A cross E? It's just if A was alpha 1 from alpha n, and this is alpha 1 epsilon, alpha 2 epsilon, so on, right? What's the size of this? What's the size of that? Yeah, not 1, but same as the size of alpha 1, right? Alpha 1 didn't have size 1, but yeah, whatever the size of alpha 1 is, it's that, because it's just the sum size of alpha 1 plus the size of epsilon is 0, so it like doesn't add anything to the size. Okay. Are people actually following? Because
Can you take the definition of size of like A cross B, like A comma B?
Yeah, I defined that, right? The size of alpha beta, like alpha beta is an element of A cross B.
Yeah.
I defined the size of this to be the size of alpha plus the size of beta. That's how we got that product of generating functions thing, right?
Okay.
Okay. So So it's clear that A cross E, so the generating function of, okay, so yeah, the generating function of E is just one. One element of size 0, nothing else. So the generating function of A cross E is the same as the generating function of A. Because you're not changing the size of the element. If I just write alpha 1, alpha 2 here, the coefficients of either each one will be the same. Or if you like it, you can actually just say this generating function is Az times Ez. Ez is 1. 1 is the generating function identity, so it becomes Az. So in any case, this A cross E is useful in the sense that if I actually had to add A and B, but this stupid union problem was coming if they had common elements, I'll just do this. Take some epsilon 1, B cross E2, there are two of this kind of set, beta 1, epsilon 2, so on, right? Now, these two things have nothing in common because epsilon 1 is not epsilon 2. So there's no way that one of these pairs could match. Two of these pairs could match. Right? Because you'll compare pairs tuple by tuple, element by element. There's no way there are some equals. So if you take these union, their union, you'll get all these elements. So alpha 1, epsilon 1 is essentially alpha 1, but with something that like separates it from some possible beta i's which also have the same value as alpha 1. So that's why these things are useful here. So in the sense that 1, 2, 3 class and that 3, 2, 3, 400, that 3, 4 graph class, actually when you do the cross, 3 epsilon 1 is one member, 3 epsilon 2 is one member. These are not equal. So when you take this union, so I'll define this A plus B as A cross E1 union B cross E2. Now you see that both these copies of 3 are retained, right? We'll still treat, like for our own convenience in conversing or whatever to do, we'll still treat A1 E1, A1 epsilon 1 as alpha 1. And size is also the same. There's no difference, except that it somehow demarcates that this came from A. And like, you should never like merge it with other elements of B, right? So, do you see that now these are disjoint and their union does not lose any elements of A or B? Okay, so this is the definition which gives the following. Is it clear why C of Z equals A of Z plus B of Z?
Yeah, somewhat.
Okay, what is not clear?
Like if you're like just demarcating, like if you're using A cross epsilon 1 and B cross epsilon 2, then
Okay.
like what's the point of taking A plus B? Like you are anyways writing out like each of them individually in each term, right?
This notation A plus B, this A plus B is just notation. I mean, there are two classes. What plus is there on them? I want this kind of thing to hold, and to make the notation for the sum, I could have called it sum of A and B. I mean, if I wanted, but just because that has a plus, you call this. Like the actual thing you're doing is only this, right?
Oh, fine. Okay, I see. Yeah.
So it's not. It's just a lot of it is notation, but you see what the underlying thing we're trying to do.
Yeah, fine. Now I see. Okay.
Okay. Even this A cross B, in this case, it's okay because it was actually the Cartesian product itself. Like that also has the same symbol, but here it was slightly different, just to ensure there are no merges. Okay. Yeah. Now we get to the one of the most interesting constructions, sequence. Okay. First, sequence construction. Let B be a class, then you define this class sequence of B. Again, this is notation in the sense sequence of B is what you write like in English, but sequence of B is a class which we'll define in terms of B. Okay, it's just notation to show something being done on B, right? Okay, so I mean, what do you think sequence is? Okay, if I give the definition, is it clear?
Yeah.
Right. So what is sequence of B?
Like the set of all elements from like which contains like B1 and then B1, B2, B1, B2, B3, stuff like that.
Yeah. So the thing is like the set of all permutations we just called, I mean, it's the class of all permutations. There's no mention of permutations of size n. That's what is different from the usual way of looking at it and this one. So in this case, you don't care what the size is, but it's just the set of all sequences, class of all sequences with elements from B. Right? That's what you understood also, I think.
Why is it permutations? Like you're just taking like the first
No.
element and
Oh, I just meant I mean, the way you call this sequence is the class of all sequences with elements in B. Like not in a sense as one element, then two element, three element. Just the way you
yeah.
talk about it. Right? Because you won't say that the set of all permutations. That's a different class. The set of all permutations is, I mean, all one permutations, two permutations, three. Just say all permutations. I mean, 1, 3, 2 is a permutation. You don't care it's a permutation of what.
Okay, so like in this sequence we said something like B1, B3, B2 won't be there, right?
It will, right?
Like the indices are in order, right? Like B1, B2, then B1, B2, B3.
Oh, these are just elements of B. They might be the same element. They might be.
Oh, fine. Okay, I see. Yeah, okay.
Some things like K elements of B, you put them in a tuple, essentially that. Right? For any K. So they're the set of all finite sequences with elements in B. Okay. So for example, if B was 0, 1, then so this could be the empty thing also if K is 0. Empty tuple is the same. It's called phi as well. So and also the size, since it's a class, I have to define a size. The size of this is just the sum of all the sizes, okay, of all of these elements of B. So if B is 0, 1, then the set, like sequence of B is this plus 0, tuple. Yeah. This plus is just, I mean, this plus doesn't stand for anything. It just is like more elements are there. It's and. You see where this is going, right? You get essentially sequence of B is like for this particular B is like it's very similar to the set of all binary strings, right? You see, this is the empty binary string. This is the string 0, this is string 1, this is 0, 0, this is 0, 1. So on, right? You see, this is sequence of B, right? As constructed. Hey, people in the chat, please.
Yeah,
Like
I
and see.
somewhat see that. Yeah.
Is everybody following? Because once we do this, you'll really like the applications because they're like one-line proofs of most results you have seen so far. Once you get like what is it trying to do. Okay. Can someone just say in the chat that they're following? Phi is the empty tuple. Like I said, k could be 0. So you just say it's the empty tuple also. Just add that. Right. Okay, cool. So now the interesting thing is that this is very similar. So the instead of saying very similar, I'll use a word called isomorphic. And two classes A and B are isomorphic. You write this if they're like an is equal to bn for all n. Many ways to look at it. I mean, an equal to bn for all n, or their generating functions are equal. There's another way which is called there's a size preserving bijection between them, which means there's a bijection between these two sets and an element alpha gets mapped to beta where both their sizes are same. Then you see that this also holds, but yeah, that's not relevant right now. Okay, so this is what we'll use, and you see that this phi empty tuple has size obviously 0 because size was defined as the sum. Sum is 0. So this has size 0. So it's isomorphic to this class, which is also which we already called E, right? Because both have the generating functions 1. I mean, isomorphic, you can just say same size classes. It's just easier to use this symbol. Okay, and these one strings are like these one size tuples are isomorphic to B, right? Nothing much, just remove the brackets. Yeah, and these are isomorphic to this class, B cross B. Do you see that? Is it clear why these three are isomorphic to these?
It's clear.
Okay, cool. Now you have this 0, 0, 0. I won't bother writing the parentheses. You have all these till 1, 1, 1. This is isomorphic to B cross B cross B. You see that? Right? Because B cross B is like B1, B2, B3. You can just remove whatever parentheses, the inner parentheses. Like a tuple maintains its order. So you can't change around the order. Like the order matters. So this is essentially the same as this, right? It's just written with more parentheses.
I didn't catch that. Could you try again?
Second. Right. So you see why these three size tuples are isomorphic to this thing.
Yeah.
Okay. So in general, this whole thing proceeds. Just remove lot of tuples. Like the 4 ones will be B cross, B cross, B cross, B. So on. Just remove the parentheses that are not required. And then you can see that this is epsilon plus. This is that combinatorial class plus which we did, which for now you can just look at like adding the generating functions or add the elements of the same size. No parentheses required. So I'll omit these parentheses for now. So on. Okay. Why? Because this particular thing is just empty string or epsilon 0. Actually, to be even more careful, you remember we did the putting epsilon stuff so that there are no overlaps. So ideally this would be like this. More 2 of these and then 8 of these and so on, right? But I mean, we can distinguish tuples. There are no overlaps in this case. So just so that I don't go mad writing these epsilons, I'll just call it 0, 1, 0, 1, 0, 0, 0, 1. It's understood those epsilons are always tagging there, but we don't really care here because we won't mix them anyways. So sequence B is essentially this. Because each of the elements of sequence B was actually isomorphic, in the sense these 3 tuples were not this. They are not exactly this, but they were isomorphic to it. You should actually say this, but it's fine. So in generating functions, this is 1 plus, because the generating functions add, plus B of Z. That's its generating function. What's the generating function of B cross B? B of Z times B of Z. What's the generating function of B cross B? I mean, it's fairly trivial to see, like you can even guess. But do you see exactly why it's a cube? Just trying to make sure.
It's like these are like all the 3 tuples, right?
Yes. So
Oh. Like by definition, it should be like BZ cube, right?
but what was the definition? There's one cross here. Yes, we know that in cross, the generating functions multiply.
Yeah. So polynomial multiplication is defined, right? In this
No, that's okay, but I just want it to be clear that this is actually a double application of the multiplication thing, right? Usually for numbers, you don't really care. I mean, you just write 2 times 3 times 5, but just to ensure, like, I mean, that you're only using whatever was taught before, whatever we had already defined. Just making sure, right? So, sorry, I might be a little picky on that, but yeah. So, okay. Is this clear?
what is that like thing?
Sorry.
Minus
1 by 1 minus BZ.
BZ, right?
Yes.
Yeah, fine.
So, so one point to note. See, again, some reason for being picky, but that if BZ had an element, if B had an element of size 0, okay, then in sequence of B, suppose that element was called I mean beta 0, and it had a size of 0, then sequence of B has empty string, this tuple, this double tuple, triple, and all of them of all of size 0, which means that it has infinitely many elements of size 0. That violates what we said about a class, right? It must have a finite number of each. Why that finiteness we look at when we look at applications, but you see that if there was this kind of beta 0, then to any tuple you can just add, you can sprinkle as many other of beta 0s you want and extend the tuple, and the size won't change, and you'll get infinite number of each size. So that's not good.
Yeah.
So we define sequence of B only if beta Z has all elements of size at least 1. Only then this is all finite. Okay. And in that case, I already told you, right? So this function here, 1 plus bz, all that, this formal series, once you expand out everything, notice that its constant term is exactly 1. Right? This starts from z or z square, whatever. It doesn't have a constant and so on. So this thing has a non-zero constant term, and so it can be inverted. And that same argument which we did, 1 minus bz, 1 plus this thing, again 1 plus b, and then minus b square will show that it's in fact the inverse. Yeah. So the sequence is defined when b0 has no element of size 0, and in that case sequence of b has the generating function qb of z, where q of a formal series f is the formal series 1 by 1 minus f. Right? Is that clear? Where? Okay. So q of f is the inverse of 1 minus f, and 1 minus f can be inverted because its constant term is 1, non-zero. And this is just because b must have no element of.
What does this thing mean? The thing which you wrote on right, like z0 brackets f0.
That is coefficient. The coefficient of zn, meaning, like if f is an, then an is zn of f.
Ah.
This is the coefficient.
So yeah, the constant term should be 0, right? For this.
Okay, so this has some terminology. This thing, this q of an f is not the inverse of f. It's the inverse of 1 minus f. Just has a name. It's called the quasi-inverse of f. Okay, not an inverse, but it's somewhat similar. It's some kind of inverse. Okay, anyways. So there's another construction which we won't see here because of lack of time. But now we look at applications. I must have bored you for so long with definitions, but now you'll see the power of these. Okay. So the set, so consider this class. Just has some, it's called, it's a dot or some one-sized graph or whatever it is. It's some object that I don't really want to waste my time drawing bigger. But it's a class with one element, and I'll define the size of this element to be 1. Now, z cross z, which I'll sometimes write z square, is exactly this, right? The Cartesian product of one element set is just that. So z is actually isomorphic to 1, right? Where 1 is a class, where the size of 1 is 1.
Yeah.
And z square is isomorphic to this class, where the size of 2 is 2. So on. So sequence of z is actually isomorphic to the set of non-negative integers with that usual size of like I is just I, right?
Yes.
Why isomorphic? Because what's the generating function of this? It has 1 of every size, 1 empty, 1 1 1 2. This also has exactly that. You can compute from the generating function if you like as well. Z has the generating function just z, right? 1z. So sequence has coefficient 0 and stuff, so you can constant coefficient 0, so you can invert. 1 by 1 minus z is the inverse, which is 1 plus z square, so on. It's the same as generating function of that. So if the generating functions are equal, every term is equal, and so they're isomorphic. Yeah. So just from using this and our operations, you can define the set of integers. Okay. Now we look at composition. Okay. Actually, it's the time. Okay. Oh, just give me a second. Okay. Right. So now this standard problem. So a composition of n is a tuple x1, x2, xn, each greater or equal 0, with x1 plus x2 plus xn equals not n then, xr is n, right? I'm pretty sure most of you have seen this problem. Find the number of non-negative solutions and stuff like that. Right?
Yeah.
Yeah. Okay.
It's like n plus r minus 1, choose r minus 1.
So, okay. Before we move on to this, do you guys, like the people who have already seen generating functions, do you know what this is equal to?
There used to be a nice closed form. It's like the rth term is k plus r minus 1, choose r minus 1.
That's not 1. I mean, if you put k equal to 1, you will get back, this will just be 1. So it's a nice exercise to try and show, as in, I mean, it's very easy. Like, you just have to show this, right? 1 minus z per k, summation that thing, z per r. This you just expand using binomial, this thing, and just show that the thing is 0. It's non-trivial, but it's not that hard to show. Leave that as an exercise. And keep this identity, we'll be using this. So notice this just came straight from a generating function inverse. Okay. Now, so you're looking at these tuples. I want to know the number of solutions to this. Consider the class of all compositions, right? When I say consider the class of all compositions, I'll call that C. What do you think C is, like, as a definition? Okay, wait.
It's like the first. How do you
Go on.
The first thing is like just n, and then you will have like n comma 0, n minus 1 comma 1, stuff like that, right?
Oh no, I mean, like, as just as a set definition.
So then like x1 so until xr such that summation xi is n.
That's the thing, right? It is the generality of it. That you don't really care that the sum is n. I'll define my sum. Like, what was our definition of size?
Like size of x1 plus size of x2 plus so on.
So I'll just say, I want the number of elements of size n. Now that's easy. I mean, it's just that number Cn and stuff if I can find the generating function.
Right. Yeah.
So it's just this such that each xi is greater than equal to 0. Or it's in that I class, which we already found before. Correct? Set of non-negative integers. So this is the set of all compositions. We're only interested in the compositions that have size n. Right? Is that clear? So we're interested in this class Cn, and actually, I mean, we don't really care about the elements of Cn. We don't want what those values in the tuples are, but we just want the number small cn. Is that clear? So this is how a problem will usually be solved.
Can you tell me what capital Cn was and small
Capital Cn is the set gamma in C such that the size is n.
And that's what we want, right?
That's what we want. And ideally, we don't even want capital C. We just want a number.
Oh, fine. Okay.
Right?
Yeah.
So the thing is, do I know a generating function for this? Or do I know how to express it? Do I know how to specify it in terms of, or like give an expression for it in terms of things whose generating functions I already know? Okay, wait, the first example, so I should probably. Do you see this?
Yes.
This was the definition.
Yeah.
All right. Here's the even better thing. What was I? I had the generating function
1 by 1
z plus so on, right? So it's just this.
Yeah.
Okay. And
oh, right. And we are picking like the rth term. So we go to like something like that, right? Like we want the like nth term. So in sequence, like in capital C, that will be 1 by 1 minus z to the power n.
1 minus. Yes. That's true, but I mean, think about it. Right, that's true, but how will you arrive at it just from this? In a sense, like the way you're looking at it is a bit ad hoc in the sense that it probably doesn't work for the next problem, right? You're looking at it at a case by case. Like the thing I'm trying to motivate is how to just look at it from this, so that it's much easy. I mean, it's more mechanical in a sense. You don't have to really think for the same thing. Like there could be a class D which is sequence of C. And would you know how to deal with that? This may be very hard to interpret.
Yeah.
Do you get the thing we're trying to address? We don't want to interpret it on a case by case basis. We want to interpret it straight from this kind of equation relating a class to smaller classes is like a specification of the class. I mean, you could just say a composition of n is a sequence of non-negative integers, right? Should write this better. A composition, I should remove this off n, is a sequence of non-negative integers. That's all it is, right?
Yeah.
So the nice thing about this is that this is exactly what's given to you in the question. And this is what comes out of it. I mean, there's nothing much we did. We just wrote this English thing in this sense. Right? Do you follow that?
Yes.
So if I say, I mean, a domino class is, or I mean, whatever you want, a dinosaur is just a sequence of compositions, then you get this straight away from this, right? Instead of I, this will just be C. So you see that the English tells you what this is. And then you can let generating functions do the rest of the work for you. You know I of Z, just you know what sequence means, like how the generating functions come. And then you will get the generating functions for C or D or whatever. That's the general idea of it. Is that clear? It is quite vague, so let us actually work out C of this thing. Okay, that's fine. Okay. Now again, the problem with this. Okay, actually, I made a slight mistake. A composition is a sequence of positive integers, because that similar problem is there. No, if I allow zeros, then for n0, n00, all of them are compositions, and then there's nothing in the number of compositions. It's infinity. So I'll allow only positive integers. That's fine, right?
Yes.
Okay, good. So now the set of all positive integers n has the generating function z plus z square plus 1. Only 0 is not there, right? So it's z by 1 minus z. That's clear? It's z times of 1 plus that thing. 1 plus z square, so on. Okay, it's done. So now composition is actually, my bad, it's not sequence of I, it's sequence of n. Is that clear? I just wrote English in this. So sequence of n. So obviously Cz is just, Cn, the number I want is this, correct? And Cz is just 1 by that. Nz is that. So 1 by 1 minus z by 1 minus z, 1 minus z by 1 minus 2z. This 1 minus z. Correct? So z power n in this I want. Fair? Which is, we know the expansion. 1 minus z, 1 plus 2z plus 2 square z plus 2 cube z. So on. Sorry, 2 square z square, 2 cube z cube. Which, can anyone tell me what this coefficient is? Simple extraction from a generating function. Anyone? Or if you haven't followed till this place, tell me where it broke off. I'll repeat that argument.
Well, it should be like 2 power n minus 2 power n minus 1. So like 2 power n minus 1.
Exactly. You could also have gotten that from writing this 1 minus z as 1 minus 2z plus z. So like, yeah, but either way. So it's 2 to the n minus 1, right? And
Can you tell how 1 by 1 minus nz is 1 minus z by 1 minus 2z?
oh,
Oh, fine. Okay. Yeah.
so I've just made it mechanical in the sense, I mean, or not mechanical, but like computable. The nice thing about this is you can't tell a computer use stars and bars and solve this problem for me, or use some other method and um, so we'll show by stars and bars also that you get 2 to the n minus 1. It's a sum of binomial coefficients. But in the sense, you cannot tell a computer that use stars and bars or use this. Yes, you could tell the summation, I mean, say, do the following from stars and bars, like which is what we'll do. But the problem is you have already used stars and bars, and that's like the human's work. In this case, all I tell it is the definition of a composition, and then I mean it sees okay composition, sees sequence, sees positive integers. The transformation is immediate. Now after that it knows that sequence means take 1 by 1 minus, and computers are really fast at polynomial multiplication and inversion and all that. So it like gives you the answer immediately with no work. Do you see why this is useful? Or why this may be more useful for harder problems in the sense, uh, I said, right, a dinosaur is a sequence of compositions. How many dinosaurs of size n are there? Well, it's just z to the n in this whole thing. 1 minus. First, you have to check that C0 is 0. What is C0? Oh, unfortunately, it's 1 in this case. So I cannot say it's a sequence of compositions. I will say sequence of non-empty compositions, which means we're talking about that remove that 0 object from there, or whatever, 5, right? Then that generating function will become 1 minus z by 1 minus 2z and take out a 1 from it. Okay. Then computers will find that coefficient for you. It may not be very easy to do on an Olympiad. It will take some time, but computers will do that for you immediately. Because how else would you have solved this problem? Do you see why this is different from usual? Or do you just see how just an English definition can just give you the answer?
Yes.
Right? So the nice thing about it is you've done all the work looking at this sequence. You've done all the work looking at product, dot. There are some few more this kind of things like sequence for sets and all. There are some things. But once you tell it, like, I mean, even partitions, like, which may not be very straightforward otherwise. I was going to cover that if I had time. So partitions are just a partition is what? It's a set of positive integers where you don't really care about the order, which sum up to n, right? It's sum x1, but you don't care about the order. It's just a set essentially, correct?
Can you repeat what you said? Like my net got disconnected.
Sure. So a partition of n is just a set, not a sequence, but a set of integers x1 to like xr which sum to n. Like a partition of 4 is 2 plus 2 works, 1 plus 1 plus 1 plus 1 works, 3 plus 1 works, but 3 plus 1 is the same as 1 plus 3.
Yeah.
Right?
Oh, the order is different, right? So we count them as different, no?
For compositions you do, but not for partitions, right? It's the usual partition that
Okay. Yeah.
the partition of n. Or I mean it's that like indistinguishable balls into indistinguishable bins case.
Yeah.
Yeah. So the thing is, I mean, you probably know that there's no closed form for partitions. The number of partitions of n. So now what you can write is, in this case, since 2, 1, 1 is not a set because it has repeated elements, you can call it a multiset. A multiset is just like 1 comes 2 times, 2 comes 1 time. If you have seen C++, it's a map in a sense. But the thing is, instead of sequence, there's a multi-set construction. And so all I'm saying is a partition is a multi-set of the natural numbers. So directly the n thing is just Zn in the set of partitions, in the class of partitions, which is Zn in M set of n. What M set translates in terms of generating functions is not that trivial, but you see, a computer can really quickly solve this. Is that clear?
Yeah.
Yeah, I mean, that was the main thing. You just translate English into symbols. That's why it's called the symbolic method. And there's not really much else you have to do about it. We're doing, so it looks too easy, but we are doing all the work in defining the M set and sequence, and there are some other things. But we are doing all the work there of that multiplying generating functions and showing that it's the product and stuff like that. And then rest of it follows quite easily. Okay, last thing before I close is that this 2 to the n minus 1. Let's just verify. Okay, you want x1. Let's verify classically. And then I'll show you like we're exactly doing the same thing. You want this, right? R can be anything. So the number of these is just the number like when R equal to 1, R equal to 2. Of course, R can at most be n, right? Because each one is at least 1. Is that clear? The number of compositions that sum to n is this plus this plus this, the number of solutions to each of these.
Yes.
Okay. And this is, I mean, you know this greater equal 1 thing. Like each of them is greater equal 1. So you might as well take x1 minus 1 is n minus 1. And this is at least 0. So it's that n minus 1 plus, what plus 0 to 0. This will be n minus 2 plus 1 choose 1. So on. So in general,
Yeah. So it's like sigma n minus I choose I.
Sigma, yeah, n minus 1 choose I goes 0 to n minus 1.
2 n minus 1.
Indeed. So that is essentially how you get that. And yeah, okay, I'll leave it at that. So there's other ways you could think of, like how you could actually get this summation itself. Think about, instead of using this, what if you use 1 plus nz plus nz square to find it? Yeah, but so you can verify that by normal. This is the answer. The only thing, it's just this is something you had to do to get this. Of course, you should be able to do this kind of stuff, but as in, this is more important for an Olympiad perspective, but this is more general. It will accept whatever you throw at it and still give you an answer. But that complexity of solving this way just keeps increasing. Right. Okay. Yeah, that's all there is. So the symbolic method is just English in symbols, and all the hard work is done by generating functions, and the generating function translation of the sequence and multiset and product and sum and the other constructions. There's a power set construction, there's a cycle construction. So all the work to get that is actually non-trivial, and you're doing all that work to arrive at this extremely simple equation. It just follows from the English definition. And once you have that, you can pass it to a computer. So you can even make complicated expressions, like if you write, so it was sequence of n, which is sequence of that z, right? Minus 0, of course. This was I. You could have iterated once, and then you could have all sorts of fancy things. Like the partitions are m set of sequence of z minus 0. You could do a lot of fancy things. Could take sequence 10 times, and you don't have to worry about how it's being interpreted. The work done by generating functions is quite non-trivial. Like in this, imagine having to actually go through the whole generating function procedure to do it. It's kind of a pain. But like this encodes it really easy. You only have to take care of one sequence. Then you can write anything in that form, essentially. So this is quite general, and it's very useful. And it's quite used to find this kind of thing when there's no closed form, and when it's not easy to get a direct approach like this. Yep, that's all. Thank you for listening.
Thanks a lot for the lecture.